Hello, great meeting of the day. I'm Dr. Li Ting. I come from Mianyang Normal University, Scission, China. The topic I will share with everyone is Nanopore single molecule detection of Bleomycin via Dumbbell DNA scission. This is one of the scientific studies I completed. This work is of great significance to develop convenient and sensitive quantitative detection assay for the Bleomycin, as the Bleomycin is widely used in clinical treatment. In present work, the authors described a new method for Bleomycin detection using Dumbbell DNA as probe on Nanopore sensor platform, which is based on the scission function on DNA by Bleomycin. A Dumbbell DNA with T5 base loop was chosen due to its longer dwell time and higher frequency of the blockage in the nanopore. With the addition of Bleomycin furious ions, the blockage in one of the Dumbbell DNA gradually transferred to the single-strand DNA fragment signals, and it turns out to be a quantitative relationship between the event internals and the concentration of Bleomycin in a certain range, making it a promising method for quantitative detection of Bleomycin with high selectivity and ultra-low detection limit of 0.1 nanomolar. First, I will introduce the Bleomycin. The Bleomycin is the glycopeptide-derived antibiotic isolated from the Streptomyces watercilius by Omizawa and colleagues in 1996. Since their discovery, the Bleomycin have been used clinically as the chemotherapeutic agent for treatment of a variety of cell carcinomas, testicular carcinomas, and non-Hodgkin lymphoma, and other malignancies, due to its lower myelosuppression and immunosuppression. As part of the therapeutic regimen, Bleomycin have been found to be curative for testicular cancer. However, the dosage-dependent pneumonitis appear on 46% of the total patient, which limits the therapeutic efficacy of Bleomycin. As reported, it is the ability of the sequence selectivity, oxidative cleavage of cellular DNA and RNA with cofactors of metal ion, such as furious ions, that make the Bleomycin as the anti-tumor medicine. It is known that double-strand DNA cleavage is achieved by Bleomycin conjugated with metal ions, which result in the tumor necrosis. However, the Bleomycin exists some dosage-dependent side effect of the clinical treatment, which may cause the pulmonary fibrosis and pneumonitis. Even low dosage of the Bleomycin are employed, the risk of the pulmonary toxicity could not definitely be avoided. Therefore, it is imperative to develop the method for Bleomycin detection quantitatively on the clinical treatment to monitor the Bleomycin content, which may potentially be used for the control of unpredictable toxicity. There have been various methods for quantitative detection of Bleomycin, and compared to this established method, which are based on the traditional detection platform, the Nanopore sensor technology is attracting much attention in recent years, as the Nanopore sensor is a simple, cheap, yet highly sensitive technology. Based on the Nanopore platform, sensing and analysis of single molecule level could be achieved because when a molecule impacts with the nanopore, the ion current will fluctuate and current signals could be analyzed to reveal the identity and the concentration of the molecule. Besides, the nanopore is label-free, easy for chemical modification, and has high signal-to-noise ratio. Thus, the nanopore becomes a perfect identifier and detector for single molecules such as metal ions, organic molecules, proteins, peptides, DNA, RNA, and biomolecule complexes. Attributing to its high sensitivity, nanopore sensing could gain a low limit of detection range from the nanomolar to picomolar, depending on the substrate and analysis method, which is preferable compared with traditional detection methods like electrical chemical detection (AC) and fluorescent analysis. The alpha-hemolysin protein nanopore sensor is one of the most popular nanopore sensors, which have been a promising platform for DNA sensing and structural analysis due to the unique ability of alpha-hemolysin nanopore to allow the single-strand rather than double-strand DNA to translate through it. In our present work, the nanopore sensor technology is employed for detection of bleomycin, which is based on the Scission function on DNA by bleomycin. A special Dumbbell DNA is designed and produces a stable blockage event on the nanopore sensing platform, while varied dosage of bleomycin ferrious ions is added. Blockage events of the Dumbbell DNA decrease in different degrees, and it turns out to be a quantitative relationship between the event internals and the concentration of the bleomycin in a certain range, verifying the feasibility of the method for quantitative detection of bleomycin, and compared with the existing bleomycin detection assays such as fluorescent analysis. The novel method is label-free and highly selective for bleomycin with the actual lower detection limit of 0.1 nanomolar, providing a potential application on biomedical studies and clinical diagnosis. And based on the DNA scission via bleomycin, a novel quantitative detection assay have been developed for bleomycin determination on nanopore platform. A dumbbell DNA is designed and would generate blockage event on nanopore sensor, and the blockage event internals become longer with elevated concentration of bleomycin ferrious ions. It shows a linear relationship between the bleomycin and ferrious ions concentration and event internals in the range of 0.1 nanomolar and 15 nanomolar, and an obvious interval rests within 1 macromolar, making it a potential assay for quantitative detection of bleomycin in the range between the 0.1 nanomolar and 1 macromolar with actual low detection limit of 0.1 nanomolar. Further experiments demonstrate the high sensitivity and selectivity of the assay for bleomycin, and the proposed strategy offers the real-time high sensitivity and high selectivity detection of bleomycin, and may have potential applications in biomedical and clinical studies. Thank you for everyone listening.